Well, good morning. 6th of October, 2016. It's time for Calculus 2 class, and right now I'm the only one in the room. So hopefully some of the others will be coming in soon. We're in section 7.5. That's where we're going to start today. So I'll get the slideshow set up for it, and we'll start from this current slide as soon as I can see what it is. And this is it's on it's on the next page, so we haven't even gotten there yet. We're on page 398 when they were talking about proper rational functions. And I think I brought this up last time. In order to do the method of partial fractions, you have to make sure that is a proper rational expression. Now, what do we mean by that? A rational expression, P over Q, let me get my pen activated here, okay, P over Q, that's a rational expression where P is a polynomial, Q is a polynomial, that P over Q has to be proper, and that is proper if the degree of P is less than, not even equal to, I put that by mistake, less than the degree of Q. Okay? It must be less than the degree of Q. Now, what do we mean by degree, of course? Maximum exponent in P must be less than the maximum exponent in Q. Okay? Now, here's some examples that they give. All tangled up. Let me get this right. Here's one. X squared minus 3x plus 7 divided by x fourth minus 16. Okay? Is that a proper rational expression? Okay? Now, the answer is yes, it is. Why? The degree of the numerator, 2, maximum exponent in the numerator is 2, is less than the maximum exponent in the denominator, which is 4. Now, this does lead to another issue here that they are not mentioning yet. I don't think they've mentioned it. They're going to mention it later, but I'm going to go on and mention it now. I look at that denominator and say, I can factor that, okay? It factors as x squared plus 4 times x squared minus 4. I'll look at that and say, I can factor that further. X squared plus 4 can't be factored any further, but x squared minus 4 can be factored as x plus 2 and x minus 2, okay? So, I look at that and factor. I look at that numerator and say, you know, that won't factor. Okay. Why did I waste my time doing that? Well, number one, you need to factor the denominator anyway for what we're going to do next. Okay, you'll see that. But the other reason is you want to make sure there's no common factors between the numerator and denominator. If there are, divide them away, because we don't want those common factors in there. So the two things, the one is the degree of the numerator must be less than the degree of the denominator. The secondly, they can't have any common factors. Okay? They're going to bring up that later, but not now. Okay, let's look at another example. 2x squared plus 7 over x minus 5. Is that a proper rational expression? No, it is not. Why? The degree of the numerator, 2, is greater than the degree of the denominator, 1. Okay? Well, what do you do if you have a case like this? You can't factor anything out. That numerator doesn't factor. Here's what you do. You take that and divide the denominator into the numerator, 2x squared. Remember, when you're dividing polynomials, you have to leave a space for every power of your variable. And since that numerator doesn't contain a linear term, you put in plus 0x. Then you put your plus 7. Okay? Now do your long division. X will go into 2x squared, 2x times. Multiply, 2x times x is 2x squared. 2x times minus 5 is negative 10x. Okay? Now, what we used to do in long division was subtract. Since we're dealing with signed entities, I say change signs and add. So make that a minus, that a plus, add them, and this gives you 10x, bring down the plus 7, and you do x will go into 10x plus 10 times. Now you multiply, 10 times x is 10x, 10 times minus 5 is negative 50, and this gives you change signs and add, and this gives you 57 as a remainder. What do we do with it? We write that plus 57 over your divisor, x minus 5. Well, why do we do that? Well, if in the first place we were trying to integrate that initial expression, what we do is now we integrate this expression. 2x plus 10 plus the integral of 57 over x minus 5. And both of these are dx's. Now, I separated those for a reason. I probably shouldn't have. I'm sorry, that's a dx. Probably shouldn't have. You don't require that to be changed. I just chose to do it because this is easy to integrate. This is x squared plus 10x. Okay. This one, however, I would take the 57 on the outside and leave that just a 1 here, and that is the natural 57 times the natural log of absolute value x minus 5. Oops, absolute value. And then you have your plus c. So you see, that's what you do if you have an improper rational expression. Divide the denominator into the numerator. You get a polynomial out. Generally, you'll then also have a fractional form as your remainder. Then you deal with that as you need to. Okay? So that's what you do if it's an improper fraction. Now, they talk about that later, but I wanted to show you now when they gave you that example. All right, let me clear all this out of the way, and we'll do one more. This is x minus 2 over x minus 5. Now, if you're trying to integrate that, don't even start, okay? That's an improper rational expression because those degrees are the same. The degree of the numerator is not less than the degree of the denominator. What do? The same thing we did before. We love those x minus 5s in the denominators, don't they? Divide it into x minus 2, okay? There really is a simpler way to do this, but I'll show you this way. X will go into x one time. That would be x minus 5. Change signs and add, and this gives you a 3. 3 is less than it, so that would be 1 plus 3 over x minus 5. Okay? And therefore, if you were integrating this, now you integrate that. Okay? That would be the same thing. And that would be the antiderivative of 1 dx, if these were both dx's there, okay? That would be x plus 3 times the natural log of absolute value x minus 5 plus c. Okay. You could write that answer as you could of the other one. You could take that 3 and move it up as the exponent for your x minus 5, which would be fine. The log of x minus 5 raised to the third power, or cubed. It doesn't simplify it any, but you could do it. If you were squaring that, if that had been a 2 out front, then it would simplify in a sense, because then whatever you have there squared is always positive, and you can lose the absolute value sign. So, but with a cube, that doesn't necessarily work. So that answer is perfectly fine. They weren't looking for an answer, but that's what they did. It's not a proper, the first one was not proper because the degree was the same as the numerator and denominator. Do your long division. Okay. Now, I said that wasn't the easiest way to do the problem. It probably was. It was pretty easy to do. Here's another way you could have done that one. That would be x minus 2 over x minus 5. You could write that as x over x minus 5 minus 2 over x minus 5. Okay? Now, this is no easier, but all right, good deal. I'm so glad you're here. I hate talking to myself. Makes me feel like I'm losing my mind. No, I'm just kidding. Okay. All right. Marcus is here. Nobody's here. What's that? Oh, okay. Longer, whoever it was okay. Seems like but I haven't heard any more from him. Hopefully he will be getting back, or he's following it on YouTube. I was just saying on this one that there might be an easier way to do the problem, but once I started working, I said, nah, that's not any easier, so I'm going to cross that out. Yeah, feel free to use the strip. Okay, so that's no easy. I thought I saw something that would simplify a little bit, but it would be just as complicated, in fact, maybe a little more so. It works, but there's no reason to go that way. Yeah. Okay. Now, we're on page 398. We just looked at the 3 examples there of whether they're proper or improper rational expressions. Do you know what that means? Be a proper rational expression or improper? To be a proper rational expression, page, in your book it may be a slightly different. It's right at the beginning of 7.5. Methods of partial fractions. Do you see it? Very first page. Okay. A proper rational expression is one. Is your 7.5 method of partial fractions? Okay. And proper would be that the degree of the numerator has to be less than the degree of the denominator. If it's not, if it's either greater than or equal to, then what we do is divide the denominator into the numerator, long division of polynomials. Do that, and then you'll have a polynomial plus another rational expression. That rational expression from your remainder is always proper. So that's what you do. I described that earlier. So let's move on from there. Now, the second thing, and I mentioned this before too, is suppose that P over Q. Now wait, there is a side note here. It is a fact from algebra, known as the fundamental theorem of algebra, that every polynomial Q with real coefficients can be written as a product of linear and quadratic factors with real coefficients. However, it is not always possible to find these factors explicitly. The theorem says they're there, but sometimes they're hard to get, because notice they only have to be real. That means they could be irrational, and usually irrational numbers are hard to find sometimes. Now, here's the other. So the first thing is the rational expression has to be proper. In other words, the degree of the numerator must be less than the degree of the denominator. If it's not, do your long division. You got a polynomial at the first part, and then you have a fractional form, which is always proper. If you're integrating, you can integrate the polynomial to begin with, and then integrate the remainder part. Okay? Now, the second thing is suppose first that P over Q is proper, and that the denominator Q of X factors as the product of distinct linear factors. And that's what we're just saying. Fundamental theorem of algebra guarantees it factors into linear and quadratic factors, but sometimes those are hard to find. Okay? But let's just say what they're getting at here is that the P of x over Q of x, and remember it must be proper. If it's not proper, divide and make it proper. Okay? But if it is, then you wind up with your P of x, and you divide your denominator into so many factors. And if they are linear, x minus a1 times x minus a2 times dot 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 times x minus a to the n into however many. If q is degree n, technically you should be able to get n linear factors. If you can't, leave one as a quadratic. Okay? So those roots, the a's there are your roots, and they're all distinct. And there's n of them, so that means your q had degree n, because you have n x's in there too. Then p must be the degree of p must be less than n. Then there is a partial fraction decomposition. If this is the case, then you can decompose that into A1. I wish they would use a different letter, but that's capital A1 over x minus little a1. Those a's don't have anything to do with each other. They just use the same letter, one capital and one letter, lowercase. But don't think they have to be the same number or anything. They don't, okay? Plus a2 over x minus a2 plus dot 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 up to a sub n over x minus little a sub n. Okay? And these are all added. Okay? And this is breaking it into things. If that's the case, then you can integrate those things pretty easily. This might be a bear to integrate. In fact, maybe impossible until you break it down like that. That's the key for what we're doing with partial fractions. Now, but you have to figure out what the A1, A2, A3, up to AN is. Okay? So let's actually do one. I'm going to erase all this. Okay? And let's do one they give us here. 5x squared plus x minus 28 over, now look at them, weren't they nice to you? They've already factored that denominator, x plus 1 times x minus 2 times x minus 3. Wow, that was good of them to do. Number one, is this a proper fraction? Proper rational expression? Yay or nay? Say again? Yes, it is. Why? Because the degree of the numerator is 2. Maximum exponent, 2. What would be the degree of the denominator? The 3, because you'd have x times x times x would be the largest x you'd have, that's x cubed. That is a proper rational expression. Okay? So the next thing we do, once you have it factored, which they did for you, wasn't that nice of them, thank them very much, then you say, we're going to write this as this set of fractions. A1 over x plus 1 plus A2 over x minus 2 plus A3 over x minus 3. Now again, it drives me nuts that they use the same superscript that happen to have the same numbers. That's not always going to be the case. Those a's are completely independent of what the numbers are at the bottom. So don't think that that's something special. It's not. Okay, it just happened to be on this case. Okay. Now how are we going to solve that? Well, since it's an equation and you have denominators, let's divide the least common denominator, which of course is going to be this big one, because those are all little ones, all contained in this one, so this is your common denominator. Let's multiply that on both sides of the equation. Okay? So, on this side, we're going to multiply by x plus 1 times x minus 2 times x minus 3. Okay, we're going to multiply this a1 times x plus 1 times x minus 2 times x minus 3. This a2 times x plus 1 times x minus 2 times x minus 3. I wish I'd have had a bigger board. Okay, multiply this by x plus 1 times x minus 2 times x minus 3. Okay, multiply everything on both sides of the equation by that same common denominator. What happens here? X plus 1s go out, x minus 2 go out, and x minus 3 goes out. So your left-hand side is simply your numerator, 5x squared plus x minus 28, right? Now, your right-hand side, the first fraction, the x plus 1 goes out, and that leaves you a1 times x minus 2 times x minus 3, okay? If you're tempted to multiply those together, resist the temptation. It works, but it's a long way to do it. The second fraction plus a2, here the x minus 2's go out. And that's times x plus 1 times what? X minus 3, right? The third one, plus a3. What do you lose? The x minus 3, so it's times x plus 1 times x minus 2. You're absolutely right. Okay. Now, here's where the trick comes in. And there's a part of me that says, no, you can't do this. But it works, so you can. Okay? And here's what it is. One of the easiest things to do is pick some values for x and plug into both sides of the equation. Now, what might we choose? Well, that's pretty complicated. I'm not even going to go there. But if I choose that x equal 2, this term goes to 0, right? That means all this is 0. So 0 times that is still 0. And this one goes to 0. Because x equal 2, that goes to 0. And I'm left with just that term there, right? So let's do that. X equal 2. Now, why did I have an objection to say x equal 2? Let x equal 2. Because guess what? In the original form, that was not allowed. Look at that. You can have x equal 2 because your denominator would be 0 then. But guess what? We don't care because it works, okay? We're going to do it. So let's let x equal 2. What does our equation here give us? If x equal 2, this would be 5 times 2 squared is 4 plus 2 minus 28. Now that's just a number. It's complicated, but it's just a number. Is equal to, this went away, and you're left with just plus a2 times, when x equal 2, 2 plus 1 is 3, and 2 minus 3 is negative 1, right? Right? So that gives me a minus 3a. I'm using the right-hand side, because this one over here also goes to 0. And that would be minus 3a from here is equal to, here's a plus 20, plus 2 is 22, minus 28 would be a minus 6, right? Do you see that? You got it? And divide by minus 3. Oh, I forgot. This is a2. I forgot that. Okay. Divide by minus 3. and you get A2 is equal to 2. Okay? So, up here, A2 is equal to 2. So that is going to be a 2. All right? Now, because I don't have much room, I'm going to erase some of this. We already got that written down, so let's get rid of this, and let's go to the next one. Guess what next x we're going to let? Let x equal 3. That sounds good to me. And when you plug that in here, what do you get? 5 times 9 plus 3 minus 28 is equal to, now what does x equal 3 give you? Now that goes to 0, this goes to 0, and this one doesn't, so I'm going to erase, whoa, no, that's not what I wanted. Yuck, okay. I hit the wrong button. That, oh yeah, couldn't remember what I was doing. Okay. That one doesn't have a 3 in it, so that's what we're left with. Okay. A3 times 4 times 1. Okay, so that gives me 4A3 is equal to, now let's figure out what the left-hand side is. That's 45 plus 3 will be 48 minus 28 is, say again? 45 plus 3 is 48 minus 28, 20. Okay? Right? So that makes A3 equal to 5. A3 is equal to 5. So this A3 here is now 5. Right? All right. Okay. I'm going to erase just a little bit here because I've already written it down. It's not erasing. It's driving me nuts. There we go. Finally. All right. Guess what the next one will do? Let x equal -1. Okay? Because we want that term to go to 0. So let me get my eraser here and erase the things I don't want there anymore. Okay. All right. All right. When x is -1, what's your first term? Okay, it'll be 5. Minus 1 minus 28, right? Because x equals -1. Yeah, the first one's squared, but the second one's not. It's just plus x, and x is -1. Okay, okay? And that's equal to, well, here you don't have a 1 in there, so this gives you a times negative what? 3. -3 times, my pen is driving me nuts here. There we go. Goodness gracious. All right, and the next is -4. All right, and over here, a -1 would make this 0, and would make this 0. So you don't have to worry about the other two. All right, goodness gracious. All right, so what do we have here? 5 minus 29 is negative 24 is equal to 12a. And this is A3. I keep forgetting to write down my 3. Okay. No, that's not. That's an A1. Okay, sorry about that. I forgot to write it down and I was looking at the wrong place. That's an A1. Okay. Okay, that was A1 from up here. Okay. So what does that make A1? Negative 2. Okay, so the A1 is a negative 2. So, we've used all that, so I'm going to erase all of this because I just don't have room to write anymore. So, you okay with it so far? Okay, so let's erase this and that. My erasing mechanism is not doing well. It's very, very, very slow. Sorry. It'd almost be as fast to erase it all and write it all down again, but I'm just too lazy for that. Ah, finally it all disappeared. Okay. So, our fractional form, 5x squared plus x minus 28 over this factored form, x plus 1 times x minus 2 times x minus 3 is equal to minus 2 over x plus 1 plus 2 over x minus 2 plus 5 over x minus 3. Okay? Boy, that looks a lot simpler, doesn't it? And now, if we were integrating both sides of that, if that was our original problem to integrate that thing, we said, how do you do that, you know? Then, with a dx here, what you do is integrate this, dx plus that, dx plus that, dx. Okay? And that would be, the minus 2 can come on the outside. And what's the antiderivative of 1 over x plus 1 dx? Well, the minus 2 on the outside, what's the integral of dx over x plus 1? ln. That's your natural log of, you should put an absolute value, x plus 1. That should be an absolute value bar. Plus 2 times ln of absolute value x minus 2 plus 5 times the ln of absolute value x minus 3 plus c. Now, actually, we could call that a ln of c, and I'll tell you that why. Because then you could rewrite, if you wanted this, to be ln of x plus 1 to the minus 2 power, right? Plus ln of x minus 2 to the second power plus ln of x minus 3 to the fifth power plus, and then if you did lnc, you'd have all ln's in, right? So then you can combine them and make this, if you call this ln of c, then add the ones that are plus, that'd be the log of c times x minus 2 squared. Now I can take off the parenthesis, the absolute value signs, because squaring it's going to make it positive always. This one I really should leave them on, x minus 3 to the 5th power. I bet you the book does take them off. But this one's in the denominator, so this would be x plus 1 squared again. So that's always positive. Okay. Now, you don't have to write it that way, but it's one way you could write it. Or not have the c in there and just have the c out front. C plus that. That I think is just as good. Anyway, but we weren't integrating it. I just told you that's why we do it. This may be a real bear and a half to try to integrate, but break it into partial fractions is a piece of cake. All right? Okay. But that was more than the book did. Okay? Once we found the partial fraction decomposition, we can integrate the individual terms. That's what we just did. So let's do example 1. So what I think I'll do is erase everything that's here. Okay? And here's our integral. Integrate dx over x squared minus 7x plus 10. Now, remember in the last section we did, we sort of skipped the ones on hyperbolic. So the last one before that was the trig substitutions. Remember we took something like that and completed the square and came up with some sort of a form, and then you had something in terms of inverse tangents and things like that. And that was a little awkward, but doable. Now that we know partial fractions, this should be a little bit easier. Now, what's the requirement? You've got to be able to factor that denominator. So that's job 1, see if this factors. Okay? What you think? If it does factor, the first factor is going to be x times x, right? And then the signs are going to be minus and minus, because that's plus. And what might they be? 2 and a 5. Very good. Well, if that's what that factors into, let's go over here to the side and do a little scratching here. 1 over x minus 2 times x minus 5. You can write that as a1 over x minus 2 plus a2 over x minus 5. Right? What's the next step? The trick. First part of the trick, anyway. Multiply everything on both sides by your least common denominator, which is your denominator. X minus 2 times x minus 5. Multiply a1 times x minus 2 times x minus 5. Multiply a2 times x minus 1 times, or 2 times x minus 5. Okay. Now what happens on your left-hand side? It's only 1. 1 is the loneliest number, isn't it? Okay. And next? The x minus 2's go out. So that's just going to be a1 times x minus 5. Don't try to multiply through. Leave it there. Live simply. X minus 5's go out, and you have a plus a2 times x minus 2. Okay? You remember the next step? X equal what? 5. And that will give you, left-hand side says 1 is equal to, that goes to 0, and you're left with A2 times, second? Yeah, 3. So guess what your A1 is, A2 is? One-third, yeah, exactly. Then the next trick would be x equal 2. And that would produce 1 is equal to, this time, yeah, wait one, just a second. Let's take this out. And when A is, x is 2, this goes to, oh, I didn't want to do that. I swear this thing won't change. There we go. Okay. Look at that. So aggravating. Okay. So that would be 1 is equal to, x equal to, this goes to 0. So it's equal to what? Negative 3. A2 times negative 3. I'm sorry, you're right. A1 times negative 3. Ugh, okay. So what is A1 equal to? Negative 1/3. Okay. So now we go back to our integral, and that becomes the integral of minus 1/3 times dx over x minus 2 plus 1/3, that's your A2, times the integral of, hey, come on in. Finished? Thank you. Trying to keep up with everything. Oh my goodness. I didn't keep up with this other thing. No, I didn't want you here. You're here. Okay? Just in case you were doubtful. Okay. Marcus came in earlier and I marked him, and then I was closing the door and it got marked again. Sorry. So that'd be 1/3 times dx over x minus 5, because A2 is over x minus 5. Think we can do those? That's equal to negative 1/3 times the ln of x minus 2 plus 1/3 times the ln of x minus 5. Okay? And then a plus c. Okay? Duh. Duh. Okay. Now, if you wanted to, you could rewrite this as ln of x minus 2 to the negative 1/3 power plus ln of x minus 5 to the positive 1/3 power plus c. And you could combine those first two to be ln of x minus 5 over x minus 2 to the 1/3 power. Now, technically, you still should have absolute value bars there. I wrote parentheses, it should be absolute value bars. And have that as plus c. It doesn't matter if you leave it in that form or the other. In fact, they didn't even change it. They left it in the form from the line above. But let's go back and see what they've done here, because I've been writing over it. So I'm going to erase this part right here. Ooh, that was my answer, though, wasn't it? No, it wasn't. It was close to it, but not quite. Okay. 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 Where they pick up here is what we did right here. 1 times, and they did it slightly differently. They left off all that, so there's the 1 times x minus 2 times x minus 5 times a over that plus b over that. That's basically our top line, so I'll draw some stuff out. That led to our next line, 1 equals, oh, they use A and B. I was using A1 and A2. It doesn't really matter. A times x minus 5 plus b times x minus 2. I call it A1 and A2. It doesn't matter. Okay. And then we proceed on. They finally get to this. When they go back to do it, and this is exactly what we got. Let me blow this up. Okay? So back to that original integral. After you factored it, it becomes this, which is negative 1/3 over x minus 2 plus 1/3 over that, which is exactly what we got. And then we proceeded to integrate. And this is going to a different problem. Sorry! Okay. That's a different problem. So, proceeded and came up with the same answer we did. Okay? Now we're ready for example 2. I guess I'll go and get there. It says evaluate this integral. X squared plus 2 over, and look at them, they're so nice, they factored it for us. X minus 1 times 2 times 2x minus 8 times x plus 2. And that's all times dx. Now, frankly, I find this ridiculous. Almost. I mean, not that's too strong a word. I don't think I'd ever do it that way. Does anyone want to hazard a guess why? Pay attention to this term. What do you notice? Yeah, there's a common factor of 2. I'd factor out that 2. So that makes a 1/2 out here. And then you're left with an x minus 4. And why mess around with the 2x minus 8 when an x minus 4 will work, as long as you got that 1/2 out front. So to me, they've gone to an extreme to make the problem a little more difficult. Okay? And there was no reason to do that, none whatsoever, but they did it. So I'm going to do it the way I think it should be done, and then we'll see if we get the same answer. So what I'm going to do is rewrite this as 1 over 2, because that 2 comes out, factor it out, and it can come out front, the integral of x squared plus 2 over x minus 1 times, what does that become? X minus, if you factor 2 out, x minus 4 times x plus 2. And then that's all times dx. Okay, what's your next step? Okay, did I hear you say multiply the least common denominator? So it'll be by x minus 1 times x minus 4 times x plus 2. And this would be, now let's do what they did and call them A, B, and C rather than A1, A2, and A3. Because I forget to write down the subscripts anyway. So let's make it A over what? plus b over right plus c over x plus 2. But we multiplied the left-hand side by that least common number. We got to do this one too. That's times x minus 1 times x minus 4 times x plus 2. The b is multiplied by that as well. X minus 1 times x minus 4 times x minus 2. Yuck! And the c is multiplied by x minus 1 times x minus 4 times x plus 2. Okay. Ooh, my stomach's saying it's hungry. Okay. On the left-hand side, the whole denominator goes away, which is why we multiply by the least common denominator. Make it go away. That leaves you an x squared plus 2 is equal to, wait a minute, okay, good. On the right-hand side, the x minus 1's go out, and it's a times x minus 4 times x plus 2 plus b times, here the x minus 4's go out, x minus 1 times x plus 2. And the x plus 2's go out of the c term, and that is going to be plus c times x minus 1 times x minus 4. Yuck. Okay. Now what? You choose. Let x equal 4. Okay, we'll do that. Let x equal 4. What does the left-hand side become? 18 is equal to, that one goes to 0, and that one goes to 0. Okay, that leaves you b times 3 times 6. Okay. Wait. Okay. Wait. It's supposed to be a 6, and it's not all writing. Okay. All right. What does it? B is equal to? All right. So this will be 1. Then let x equal 1. Okay. Then you have 3 is equal to, now let me pause a minute here. I've got the magical thing that I can do this. You probably can't, except my magical thing's not working too well. Okay. Okay. When x equal 1, this one goes away, and this one goes away. Okay. So you have 3 is equal to a times negative 1, you said? Right. Is that what you... No, negative 3. Right. X equal 1. Okay. And that would be negative 3 times 3. Okay, you're doing it all the way. Okay, that would be negative 9. Okay, negative 9a. So what's a equal to? Negative 1/3. Okay, and then finally we'll let x equal. Goodness gracious. Okay. Negative 2. Okay. Then our equation, let me go through and erase some things. Like this. Oops, I erased too much. That. x is equal to negative 2. This one goes to 0, and that one goes to 0. And we're left with what? Left-hand side becomes 6 is equal to c times, wait one, lost the parentheses there, c times negative 3, is that what you said? Times negative 6. Okay. Okay. So basically, here's what I'm going to do. Make that a plus, divide out the 6, and leave that a 1. Goodness gracious, this thing is so slow. Okay. Okay. And that would give you c is equal to, only it's positive 1/3, isn't it? Okay. Okay. First, the left-hand side, when x is equal to negative 2, that becomes a 4 plus 2 is 6. Okay. And that's equal, that goes to 0, that goes to 0. C times negative 3, right? Times negative 6.
Oh, yeah, it's not.
Negative,
Yeah.
times negative is positive, yeah. So the 6's go out, and then you're left with a 1/3, right? 1/3. I'll be feeling that elbow for a while, okay? So what I need to do now is go back up here, and let's erase some stuff. Hopefully it will erase a little faster than it did. No, it's not. I've erased it all, but now it disappears. Okay. This is one sorry program. I don't know what's causing this, but it is. Okay. So let's go back and plug in what we've got. This was 1/2 the integral of, oh no, that's what I needed. It was a over x minus 1, and your a was negative 1/3. So let's make a negative 1/6, because we had a 1/2 out there. Negative 1/6 dx over x minus 1. Right? Okay. Remember, my next line was to take that and do a over x minus 1 plus b over x minus 4 plus c over x plus 2. Right? So, I had a 1/2 out there, and the first integral would have been a negative 1/3 over x minus 1. Well, I had a 1/2 out there already. I put a negative 1/6, so we did a 1/3 dx over x minus 1. Okay? And then the next one would have been the b, which is 1. So that would be a plus 1/2. Remember, the 1/2 is already out there. Integral of dx over x minus 4. Plus 1/6, because 1/2 was out in front. The c is a 1/3. So that would be a 1/6 times the integral of dx over x plus 2. Sorry, I erased too much before. Okay. Now, I think I can erase these now. I sure hope so. Okay. Okay. Going going to get rid of these two because we've already written down what they were. I hope. Yuck. Sometimes it erases slow and sometimes it does pretty well. Okay. So that leaves us a negative 1/6 times the ln of x minus 1 plus 1/2 times the ln of absolute value plus 1/6 the natural log of x plus 2. Okay, and then you have a plus c. Exactly. Now, according to what they did last time, they probably are going to leave it in that form. Let's see if they do. Okay. Don't worry about the intermediate steps because they were doing that different problem. They left the 2x minus 8 in there. We didn't. But our final answer should be similar to theirs. A negative 1/6 log x minus 1, yes, plus 1/2 log x 2. Okay, they say 2x minus 8. Okay, and here's why it's okay. I'll get to it in a second. Plus 1/6 log x plus 2. Okay, now here's the difference in their answer. These answers are the same, but they do a 1/2 log of 2x minus 8, right? Which I'm going to write as 1/2 the log of 2 times x minus 4, right? You can put that in absolute value bars. Well, that is 1/2 log 2 plus log x minus 4. Okay, right? Well, 1/2 of log 2 is just some constant plus 1/2, so it's the same thing. I included in the constant there this thing plus that, so they are the same answers. Theirs is just written, I want to say stupidly, but I shouldn't say that. That's not nice, is it? But I don't see any reason to write that non-factored. So those are the same answers. Absolutely, don't sweat it. Okay. Now, now suppose that the denominator has repeated linear, oh wait, okay. Now, if you haven't noticed this already, what this line is here is exactly the line I erased. The x plus 2 over the factored form, I factored the 2 out, x minus 4 times x plus 2, and then wrote it as a over x minus 1 plus b over, I factored the 2 out, and that would be x minus 8 plus c over x plus 2. Okay, that was the line I erased already. Then when you go to the next one, when you multiply that by the least common denominator, which is that big denominator on the left, then you get an x squared plus 2 on the left times a times, I put x minus 4 plus times x plus 2 plus b times x minus 1 times x plus 2 plus c times x minus 1 times x minus 4. I factored 2 out earlier. So when you take that and then plug in x equal 4 and x equal negative 2 and x equal 1, then you get this form here. Now notice they have 1/6 there where we had 1/3, but that's because I factored the 2 out, so that's still working okay, even though it doesn't look like it would be. It It does work okay. And that's as far as they go. They just leave you hanging right there. They didn't do the integration. But they did in the book, and it came out exactly the same thing. Okay? So, I think we're ready for example 3. Can't use that pen, can I? All right. Evaluate this. The integral of, oh, wait. Okay. Sorry. Let me back off. Okay. Now suppose that the denominator has repeated linear factors. In other words, there are p of x over q of x. What are the 2 requirements of those polynomials? What about the denominator? Yeah. The degree of the denominator must be greater than the degree of the numerator. Or said the other way, the degree of the numerator has to be less than, not even equal to, less than the degree of the denominator. Okay? So that's the first thing. The second thing was they can't have any common factors. If they have common factors, get rid of them first and then proceed. Okay? And the numerator has to have a lower degree than the denominator. So we'll assume that's true. Okay? Now, what if then when you do all the work, this gives you that numerator. Notice we don't really mess with that except maybe to factor it to see if there's any common factors. But if it's not, then what if we have our our x minus, what is it called? A1, no, AI times an A. Yuck. I can't write. Okay. X minus AI squared. I'm sorry. I'll jump down the line. Let me go back up. Okay. I lost my place. In case you're wondering, it's not that I want to do it this way. I found that if I would love, because I'm left-handed, to have my book over here and the computer here. But if I do that, I start blocking the projection. So I have to have my computer over here so I don't block the projection. And therefore, I'm going crazy trying to keep up with where I am here. What's that? Yeah, the thing is, when I have a full class, I block more people when I'm over there. So over here, I don't block as many. Even you moved up there because you can see a little better than this. But if I'm out there, then I block more people. So that's why I keep it as far over here as I can. I guess I could go further, but then my cords get to stretching too far. So I guess I could do it a little bit, but if I moved it over there, then I'm blocking people because I have 2 classes that are full, not full, but take up most of the desk. Most of my classes are smaller like this. I have 3 in this one, 9 in Cal 3, 5 in differential equations, and 3 in linear algebra. So I've got a lot of small classes, so I could do it then, but I've got 3 classes that are pretty good size. One that has probably 27 or so, one that has like 21 or 2, and one that has 18. So those classes I don't want to be blocking because they have to be sitting and I'm in the way of stuff. So that's why I sit over here. Now maybe it'd be better if I did that. Okay. X minus A1 raised to the, they put strange exponents here, M1, capital M1, why I don't know, X minus A2 to the M2 dot 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 times x minus a to the n. Yeah, I want to make sure I use the same. So m to the n. Okay. What if that is our denominator? In other words, when you went to factor, you had multiplicity of factors. Okay? Not just x minus a1, x minus a2 times x minus a to the n, like we did before, but now some of these m's may be 1. That's fine, you know. But some of them may be 2 or 3 or 7 or 15 or something like that. What do you do when you have multiplicity of factors in your denominator? That's the issue. Okay? Here's what you do. And it seems strange, but it does work. Each factor, a sub I, m sub I. Okay, raised to the m sub I. Each factor then you treat separately. Okay? And now, for some reason, they go B's rather than A's. So this one right here, this one factor here, you know, it would be 1 over x minus a sub I. I'm sorry, that would be a B. B1 over x minus a sub I to the first power plus B2 over x minus a I, to the second power plus dot 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 plus b sub n, no wait, b sub m1, because that's how many powers you have of that first factor, over x minus a sub I. Why did they change the i's? If that's that first factor and you're using m1, oh, that's not m1, it's m sub I. That's why, okay. This is for any one of them, and that's raised to the m sub I power. Okay. No, m sub n power. Okay. Where n goes up to, yeah. No, I'm sorry. I'm looking at the wrong thing again. I thought, why are they doing this? This is not the way you do it. Okay. This is m sub I. Yeah. M sub 1. No, m sub I. Sorry. M sub I. Okay. Basically, any one of those. That's why they choose that. So if it was the first one or the second one or the third one, any one of those, you split up this way. Okay? If it's raised, give me a number for m. Make up a number. Yeah. 4. Okay? So let's say this is x minus a1 raised to the 4th power. Then you would be, say, b1 over x minus a1 plus b2 over x minus a1 squared plus b3 over x minus a1 cubed plus b4 over x minus a1 to the 4th power. You go up to that and you have a single letter over the first power, second power, third power until you get to the nth power. Okay? That's what it means. And you do it for every one of these. You know, if that was your 1s, then you do it for your 2s. You use different letters here, of course. Then you do it for your 3s and as many as you got. Frankly, you're not going to have that many. Okay, usually just 1 will have multiplicity, maybe 2, but not a whole bunch of them. Okay, that's the generic form. Let's go to example 3. So I think I'll erase all this just because it's too confusing. Okay, and let's do example 3. Evaluate this. The integral of 3x minus 9, and again that irritates me, 3x minus 9 over x minus 1 times x plus 2 squared dx. Okay? Anyone want to guess what irritates me? Yeah, 3x minus 9. Why do that? Take the 3 outside. Keep it simple. I don't know why they don't. So I'm going to do it this way. The book will do it the other way. I think we'll get the same answers. That will be 3 times the integral of x minus 3 over x minus 1 times x plus 2 squared dx. Okay? Now, no common factors. What's the degree of the numerator? Okay, numerator. 1, and the denominator is 3. You're absolutely right. Because this is squared, that'll give you maximum exponent of 2 here, 1 there, that would give you 3. So yeah, we have a proper form. Let's factor the 3 out. And yes, that's still proper whether you did it or not. And no common factors. So this has a factor of x minus 3, these are factors of x minus 1, x plus 2. No common factors. So we can proceed. How do you recommend we proceed? Let's write that x minus 3 over x minus 1 times x plus 2 squared. And what would be our breakdown of that? Basically, yes. With the one exception that you have of multiple power. Okay? Okay, I've already written that side. So over on this side, it would be a over x minus 1 plus b over x plus 2 to the first power plus c. Now they probably do b1 and b2. Why not do c? Okay, over x plus 2 squared. Okay, when you have multiple powers, you just keep going. They probably do b1 and b2, but it doesn't matter what you call it. To me, it's easier to do a, b, and c because I don't forget to put my subscript in. But that's what you have. Okay, what's next? Flagging up again, sorry. Yes, multiply both sides by your least common denominator, which will be x minus 1 times x plus 2 squared. 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 Okay? The left-hand side is relatively easy. X minus 1s go out, x plus 2 squareds go out. Everything's gone but x minus 3, which is what you had to begin with. And that's equal to, in this one, the x minus 1s go out, and that leaves you an a times x plus 2 squared. Plus, here, one of the x plus 2's go out, and it leaves you with a b times x minus 1 times x plus 2. And over here, both of the x plus 2's go out, it leaves you a c times x minus 1. Okay. Got rid of all your denominators, the big one and all the little ones. Okay? Now, what you reckon the next step is? Equal negative 2? I like it. So what will your left-hand side become? A little louder? Negative 5, isn't it? Yeah. Okay. All right. Equal to, when x equals negative 2, That goes to 0. That goes to 0. Okay, so you're left with just simply C times because the x equal -2, that one goes out and that one goes out. Okay? -3. So this implies that C is equal to 5/3. Nice pretty fraction. Don't you love them? All right, next. Let x equal 1. And what does the left-hand side become? -2 is equal to, okay, let me go back, and all that I marked out I need to unmark out, okay? And when x equal 1, this goes away, and this goes away, right? And what are we left with now? A times 9. So that implies that A is equal to -2/9. But we have a problem, don't we, Houston? We have no way of figuring out what our B is. Do we? Okay, because when you let x equal -2, you lost 2 of those. When you let x equal -1, or 1, you lost 2 of them. But you never could figure out what the B is. Okay, so what do we do with this? Okay, here we have to do a slightly different thing. Okay, and that thing is go back to this line right here, and we've got to carry it out in gory detail now. Let's get that out of the way and this out of the way. Okay, and what we're going to do, unfortunately, is this. X minus 3 is equal to, we got to multiply things out, you know, that kind of stuff. So this will, well, wait. Let's not get too carried away here. Let's plug in what the A is. That's -2/9 times, and let's square that binomial. What would that be? X square the binomial, x plus 2 squared. X squared plus, second, plus 4x, you're right, plus 4, okay, plus b times, multiply that binomial, FOIL that, what do you get? X squared isn't it plus x? Okay. Minus 2 plus, and we know what C is, 5/3 times x minus 1. Sort of a big boo hiss here, isn't it? Okay. So let's proceed. X minus 3 is equal to -2/9 x squared minus 8/9 x minus 8/9 plus bx squared plus bx minus 2b plus 5/3 x minus 5/3. Do you agree? Okay. Now, it doesn't matter which term you take. If one's easier than another, go for it. But let's just take the x squared terms. What's the x squared term on this side? No, there isn't one. Yeah, that's an x minus 3. There is no x squared term. So that's going to be 0 on the left is equal to, now what the x squared terms on this side? Minus 2/9 plus b. Those are the only two x squared terms on the right-hand side, right? So that means that b is equal to positive 2/9. Okay. Now you could have done it another way if you wanted to. You could have taken the x terms. The coefficient here is 1. There would be minus 8/9 plus b plus 5/3. Mess around with those. You should get the same 2/9. Or you could take the constant term, negative 3 is equal to minus 8/9 minus 2b minus 5/3. Mess around with that, and you should get the same answer. To me, the square terms were the easiest that came out, much easier. So b is equal to 2/9. Okay, let's see if I can deal with this without erasing what I really want to keep. Okay? So I'm going to go in here and erase certain things. Okay? And here's what I'm going to erase. I'm going to erase that and those two lines and that one and that and this and this and that and this and that. Okay. Now I think I'll erase everything below it. I sure hope I can without damaging anything. Alright. Whoa, let me not go too far. I'll do this down to here. Oh, please. I did do too much, didn't I? I lost my C. But y'all got it, right? Okay. So what that's going to be, so this numerator, which is what we had up here, is equal to, the A is minus 2/9 over x minus 1 plus 2/9 over x plus 2 plus, and what was my C? 3/5? 5/3, I mean 5/3 plus 5/3 over x plus 2 squared, right? So we take this integral that we had, and that's going to be 3 times, and instead of that thing, we're going to put this. And the first thing is going to be, first, a minus 2/9 times that, so that will make that 3 become a minus 2/3, right? I'm going to multiply a minus 2/9 times 3, that gives me a minus 2/3, right? And that's going to be the integral of, well, we can just go on it. Well, no, let's hang on to it. I'll go on and evaluate it because I just don't have enough room. Okay. Okay. I hope I'm not skipping too many steps. That's going to be the log of x minus 1. Isn't it? Okay. And then we have a 3 times a 2/9, which is going to be a plus 2/3. And the integral of that is the log of absolute value x plus 2. Right? And then the last one is going to be a plus 5, because it's 3 times 5/3. It'll be a plus 5 times the integral. This time I'm going to write it out of, that would be 1 over that, which would be x plus 2 to the minus 2 dx. Now, I just rewrote that in that way. So that's not a log. What is that going to be? Okay, I think I've got everything taken care of, so I'm going, while y'all are thinking of, while y'all are thinking about it, I'm going to erase some of this stuff. I hope I don't erase too much here. Y'all thought? What's that last integral going to be? Second? You got it. Okay. That's going to be, this one will equal 5 over x plus 2. Okay. With a minus. Okay. Why is that? Because you can do it, use substitution if you wanted to, let u equal this, du would be dx, okay? So that would be u to the minus 2 dx, and antiderivative is u to the minus 1 over minus 1. So 5, and the u is 1 over u, which is 1 over x plus 2. 5 out front, so it's a minus. Okay. So that's what it turns out being. And then you have your plus c. Okay, so the answer to this should be I'll leave it the way I think it is, minus 2/3 log absolute value x minus 1 plus 2/3 log absolute value x plus 2 minus 5 over x plus 2 plus c. Okay? How close to it did they get? Minus 2/3 log x minus 1 plus 2/3 log x plus 2 minus 5 over x plus 2 plus c. And that's by taking that 3 out and not having to fiddle with that. So you see, when they do it, they get lots of other numbers there. But taking the 3 out, I think, makes it easier. Okay. Are we running out of time? Oh, how sad. You could have given me better news than that. Okay. So we'll pick up next time with, let's see what slide we're on. We've already done that one. They kept the 3x minus 9 in there. They kept it in there. Boy, where did that come from? Wow, that's pages away. That's quadratic factors, so we're quite a bit away from there. What we're going to do is if P over Q is not proper. I've already told you what that is, but we're going to work it out and do an example with it. So that's on page 401. Homework exercises here. I know you want some of these. Do number 1 and or 3, either 5 or 7. Or both, any of the odds 6 through 45. Okay, that should keep you busy. Okay, let's hold off that for a minute. Let's just go 6 through 31. and we'll pick the rest of those next time. Okay? All right, good deal. We'll see you next week. Have a good weekend. You still listening? All right. Hope he's able to follow.